Hello, everyone. Welcome to week 2, Introduction to GIS. Okay, so first, let me share my screen to show you what to do this week. Some housekeeping thing. Okay. All right, Brian just have give me a very good suggestion. Maybe I can provide the Zoom link at the very top of our class.
Yes.
I'm going to try that. Maybe at another module head over here and provide the link just right here. Okay. And yeah, and then we finished week 1. Okay. And the last thing you want to do basically is a quiz. It's due on this Sunday by midnight. Okay. So Grayson just asked a question: how to study for this quiz? Well, my suggestion is you use lecture presentation as a skeleton, as an outline for your study, and try to first use lecture presentation because it's shorter, it's condensed, okay? And you can find the key information to answer all the questions I listed in the study guide, the study question, okay? If you cannot find it, I recommend you go for the videos and the readings on our study guide, this page. Okay, so this page provides you more than you need for the quiz, but you can learn more details. Okay, you can learn more details. So the study questions basically is right here, lecture 1 and 2 review questions. Okay, best luck on the quiz. Okay, but don't overthink my question. Jing's question is simple, easy, straightforward. Okay. All right, so let's go back to home. And when you finish, we basically finish the introduction. In this introduction module, the key thing we learn is what is GIS and what GIS can do, right? And this week, we are going to shift the gear, okay? Focus on another very important topic, understand spatial data and information, see how GIS can help us to, collect the data and also process the data, extract the useful information and wisdom for our, project and purpose to support, for example, decision making. Okay, so here is your to-do list. Okay. Let me make it a little bit smaller. Okay, here we go. All right, so like I said, in this week, we are going to dive into the important concept in GIS, data and information. To be more specific, we are going to study spatial data and spatial information. So what makes spatial special, right? Last week I shared that quotation in GIS, that is location, right? So in your data, you must have some information about location, where it is. Okay, so before getting started, I would like to ask you to recall the 4 aspects of geographic information we learned on Thursday. That is what? That is here. Location, thematic attributes. What is topology, guys? Can anyone remind me?
Isn't that what the features on the land are? Like if there's a hill or like a mountain or something like that?
No,
it's the relationship between different spaces.
Yes, but Grayson just made a beautiful mistake. I like that. Let's celebrate that mistake. That one is called topography. It's not topology. Yes, topology, that is a relationship, like Violet said, that is a spatial relationship between different, features, like your house and some street, right? Like LA County and Orange County. We have some spatial relationship. That is topology. But the shape of the land, we call that topography. Graphy means draw, right? You draw the shape, depict the shape of the land. That's a topography. outdoor people, you must like the topographic map, right? While you're hiking, that can save people's life. You won't dry out of the cliff, right? Okay, and time. But those two, location and thematic attributes, those two you must have. Okay, you must have. Topology is optional. It's optional. Not all the data you download out there online contain topological information, but they must have location and thematic attributes, or some people also called it non-spatial information or aspatial information. A means not spatial. Okay, A, just the letter A, aspatial. Well, usually your aspatial information, your non-spatial information, thematic attributes, it's it's stored in a spreadsheet, okay? But your it may contain two columns, to show you X and Y, that actually allow you can convert that spreadsheet to, GIS data layers. And you can bring that in GIS software. But it doesn't mean that spreadsheet is a geographic data layer, okay? You need to use GIS to turn that data into the data layers GIS software can use, okay? Let me show you one example. Yesterday, I download this. First, let me first show you the map, because data is boring at the first glance, but data is awesome. Okay, so this data is called literati. Literati is a map about trash, about litter, globally, and they use the the data contributed by you and me. Do you have a phone? You can contribute to this project. Okay, so let me zoom in to LA to United States. Come on. I don't know why it doesn't show. Okay, here we go. Okay, let me address your question later. Okay. Okay, let me go back. Let's see, maybe this one. Okay, so it's supposed to be like this. Maybe my internet issue, but is this a map? No. Okay, solution. Okay, I don't know why it doesn't show now. But let's see. It should be somewhere like this. Let's see. Someone can help me? No. Okay. All right. So it's supposed to be like this medium trash collection. Okay, this is the trash. And please give me a map. Oh, this is a video. Oh, here we go. Yes. So it's supposed to be like this. Show you the data where people contribute the most of the data, the litter. And they do have a, a classification about different litters, like cigarette butt and plastic and, like something, like battery. Okay, they spot on the street and they can plot it on the map to show you where you see most of the trash. Okay, let me show you another one. It's called purple air. I hope this one works. Okay, here we go. Okay, this one use the same idea. You know, people can mount a device on their house and they can help monitor the air condition, for example, PM 2.5 in LA globally. And that data automatically submit, okay, upload to this website called Purple Air. And you will see the air condition in the real time. That is now in LA, guys. In the Central Valley, it's pretty bad. I think it's because the fire, right? It's because the fire. And you can see, this is Los Angeles. And with what we are seeing now is US EPA defined PM 2.5 AQI, Air Quality Index. And you can see it's okay, it's yellow, right? It's okay, but you know, you do have downtown LA have you know, some bad data over there. Okay. Well, if you want, actually, I want to do this. Okay, you can download the data. You can see here is a little button. Let me annotate it right here. Okay, do you see this little download? Okay, you can click on this download and you can, for example, let's see, you can specify the date, okay, and starting date and end date, and you can see this is different location. You can download, you know, they have two devices, basically two monitors. One is the secondary is a backup, okay, and you can download all the data and you can make your own map. Okay, you can make your own map. That's a spreadsheet. Okay, and from the literati, if I can get the website, the point show you, it will be like this. But you can also download their data here, open data, because they collect the data using, you know, you and me. We are citizens. We call that citizen science or volunteered geographic information. Okay, another example you could look up is called iNaturalist. iNaturalist. Okay, this one is for animals and plants. For example, butterfly, for example, birds. I know out there might be a lot of, you know, bird lovers. Okay, so for example, you can explore. Let me see, let me move that around. Explore, okay, over here. Okay, you see a map. And you can see those are people contributed. Those are contributed, okay? And you can specify certain species. For example, when I'm out there, I'm so scared by the rattlesnake. So rattlesnakes, let's see. Okay, and I want to just narrow down to Los Angeles or Santa Monica. Los Angeles. Let's go with a larger location, and you hit go. Yes, and you can see those are all the submissions. Okay, those are all the submissions. You can see we have by far almost 2,000, and you can, you know, narrow down to different species. Okay, and 300, more than 300 people are there. Okay.
Jean, I have a question. Is this something that you just need your phone to, like, if I wanted to walk around my neighborhood and record like where there are frogs or something like that? Like,
exactly.
It's not like the other thing where you have to have a purpose-made device to put on your house. You can download an app, I'm assuming.
No, you just need to download an app on your phone called iNaturalist. And then you can just, you register an account first. And then you can take a picture if you spot some, you know, interesting animals or plants, okay? And then you can just submit it.
Okay, cool. Yeah, I was wondering about like more about the data collection aspect of all this, like how open source, so to speak, it is.
That's right. That is GIS, guys. That is GIS. For example, ArcGIS have this one, have something called Survey 123. Okay, Survey 123. That is a GIS software or extension or some plugin like that you can use to design website like this, okay, to allow people contribute to your database. So Survey 123 is just like an interface, like a gateway. You provide this platform for people to contribute data to your geo database. And you collect the data like iNaturalist, like Purple Air, like Literati. They collect those data and use GIS again to turn that into a map. And you can go, you know, you can do so many things there. For example, you have those spots, you can provide, you know, heat map, right, of all those submissions, okay? For example, for my Literati, you download here and their spreadsheet, it looks like this. Let me zoom into first few columns. Let's see, view, zoom to, okay, 200. Okay, here we go. And let me make the wider. Okay, and country and the date, you see that, okay? And then it needs to be smaller. So you can see, well, this basically is your identifier. It should be unique for each row, okay, for each row, because that is one submission, one observation of the trash. For example, this one is, you know, piece plastic, okay, and this one is bottle cap, okay, and this one cigarette butt. You know, every year we have the clean up the beach cleaning day, right? The largest amount of trash actually is cigarette butt. A lot of people smoking on the beach. And here you have your longitude and latitude, but don't get me wrong, this is still not your location data. It is in a column, it's waiting for you to turn this location to a point. Okay, what you need to do in this case actually is very easy. Let's see, data. Let me use another the Excel. I'm using another software to view WPS to view this table. I don't think many of you have that. Okay, let me go there. Let's use spreadsheet and show you the folder. Let's open that. We use Excel. Okay, here we go. Let me expand it. Okay, let's zoom into the few first rows. View, zoom in. Okay. Okay, go location. Okay. All right, so you can see the thing is, the problem is they store the longitude and latitude in one column. Actually, you need two to turn this data to a data layer GIS can use. Okay, let me show you a trick here in Excel. Okay, first you will need to insert a new column, you know, just after this longitude and latitude location. Okay, and then you will click on the head, click on the C, you will select the entire column. Okay, and then you're going to click on the data on the top. It's a very useful tip. I want people's attention, okay? It's very, very useful down the road when you do your, you know, later labs and your project. I bet most of you, 99% will use this tip. And then you just need to click on this one. Let me highlight. It's called text to columns. Text to columns, okay? And you click on this. you will bring up this dialog, this window, okay? You are going to choose delimited. That is, you are going to use a delimiter, sorry, delimiter to separate this column. So you can see in this case, actually it's nice. People or the data collector, they use this slash, right? This slash, yes, to separate longitude and latitude. And you just need to specify my delimiter is a slash, okay? So let me do this. Let me show you the magic. Next. And then you don't see tab. I don't want to use tab. Okay, other slash like this. And you can see in the preview window, you immediately see, oh, it's separated, right? Okay, and then you just need to click next. Actually, you just need to click finish. Okay, so you can see, let me make it a little bit smaller. You can see those two locations, those two columns, they contain latitude. You just need to change the name, and longitude. Okay, and longitude. And later you are going, you can turn this layer, this spreadsheet to data plots like this, Okay, are you curious about this? How many trash collected in LA? Well, here, yeah, this data is about since 2019, January the 1st, all the way to yesterday. I downloaded this spreadsheet yesterday to come to the trash people contributed. Okay, so if you have a few minutes later after our lecture, I'm going to turn that into a map to show you. Okay, but I want to show you. Okay, here this is your data. Okay, and you're going to use GIS. You can see GIS can help you collect the data and turn the data into information you can use, you can, understand. Okay, then the question is, what's the difference between data and information? I know Jane in her lecture, the first lecture, I see the slides, she showed these pyramids. Still remember these pyramids? I sort of like run very quickly on that slide, okay, to show you the function of GIS. She told us, well, GIS can help us collect the data, information, and to extract the knowledge, develop the wisdom, right? But what is data, in the first place? And what is the information in the first place? Why do we need to differentiate, and how GIS play a role to turn the data into information? It's a hard question, I know. Let me use a video to show you the difference, and we can relax. Jing talked too much by far. Okay, let me stop share because I need to share this video. I need to share with my computer sound, I think. Okay, share. This one.
All starts with the question, what even is information? My name's Peter, and this is Stacks and Facts. Maybe it feels like a simple question, but what actually is information? Is it the YouTube video you watch to learn about music theory? Is it the book you read in your free time, or the podcast you listen to on the bus to work? Or are these simply a medium for something else? As it happens, there's no consensus across disciplines about what information actually is, and even within the field of LIS itself, there's no single definition that people point to, but there are lots of them, link in the doobly-doo. That's due in no small part to the fact that how a mathematician thinks of information can be wildly different from, say, a wildlife biologist, whose definition is different still from a poet's, and so on and so forth, ad nauseum, forever and ever. Amen. But if we're going to talk about information science and the various information professions, then we have to give this question some thought. What we think information is and isn't shapes how we study and interact with it. So that's what we're looking at today. Now, let's begin with one of the great philosophers of our time.
Today, we're going to tell you about the word called information, right? Information. And information mean news or facts about something.
Did you catch that? News or facts about something. Now, let's see how this cookie crumbles. Okay, not this cookie. We're going to see how this cookie fits into my face. First, there's the idea of truthfulness. Information is factual. If I tell you that this is a cookie, that's information. If I tell you it's cake, that's misinformation, or at least about this cookie. It might inform you about something else, but within the context of this cookie, it's not relevant. This leads us to aboutness. Information tells us about something else. If I just sat here and said dog, magenta, Charlie Hebdo, chrysanthemum, flummox, or whatever, that wouldn't be information, it would be noise, random fluctuations that obscure or do not contain meaningful data. Finally, we have thingness, and information is a thing, albeit perhaps intangible. After all, news is a thing, and facts are things, right? They're just separate from the books and newspapers that hold them. And if we look at the roots of the word itself, we can see that this part of the definition is baked in. The prefix in means within, like in the brain or mind, and formare means to create, or take shape, or to form. Now, let's go back to Cookie Monster for a second.
Today, we're going to give you information about the word cookie. Give me cookie, please. Oh, thank you, thank you, thank you, thank you, thank you. Right in my hand. Oh, thank you. That cookie. And now let me give you information about cookie. And the information is cookie was delicious. Give me other cookie, please. Other cookie. Oh, thank you, thank you. Now let me give you more information. Cookie was delicious and crunchy. Now give me a whole box, please. Whole box. Oh boy, oh boy. Oh, thank you very much, Tara. Now, rest of information. Cookie's gone. Thank you, Tara. Give me a hug. Oh, thank you.
When Cookie Monster tells us that cookies are delicious, crunchy, and ultimately gone, it allows us to build in our own brains an idea of what those cookies are. At this point, the information about cookies transforms into knowledge about cookies, and this knowledge in turn will shape our future encounters with and perceptions of cookies as things. This way of thinking about information follows what's known as the data, information, knowledge, wisdom, or more simply, DIKW pyramid. The idea behind the DIKW pyramid is that concepts of things follow a path from least processed, like data, to most processed, like wisdom. It's an easy rabbit hole to fall into, but the basic idea is that if information were a cookie, then its ingredients would be the data that go into it, and how it tasted would be the knowledge that derives from it. Now, as for wisdom, that would probably be more along the lines of, say, whether or not a person decided the cookie tasted good or not. But that's outside of the scope of LIS, so we're not going to touch on that a whole lot. So let's move on. Now, Claude Shannon is one of the pioneers of information theory, which is a field of study separate from but related to LIS that looks at the engineering around signaling, that is, sending ones and zeros, radio waves, beams of light, and all that jazz. Shannon saw information as a thing to build systems around. He worked at Bell Labs during World War II, and like many of his contemporaries, his research initially revolved around wartime communications between entities and the systems that made this possible. The entities could be people, or they could be systems like radar or fire control. In 1948, his article, A Mathematical Theory of Communication, was published, which laid the groundwork for information theory as a field. We can get an idea of how it framed information from its introduction. The fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message, selected at another point. Frequently, the messages have meaning, that is, they refer to, or are correlated according to, some system with certain physical or conceptual entities. In other words, information is a thing that conveys meaning about stuff. Sound familiar? That gets transmitted as a message from one place to another. When we think of it this way, information becomes somewhat defined by the fact that it has a sender and a receiver, and is sent along a medium or a channel, whether that's electrons in a wire, or light through fiber optics, or radio waves through space-time. The medium may introduce interference or degradation to the message itself. You could call this interference noise like I did earlier, or entropy, which is the word that Shannon borrowed for it from physics. Shannon's model also has an encoder and a decoder. These turn the information into something that can be sent on whatever medium, say zeros and ones, and then decoded and understood by the recipient, say words or coordinates. So that's Shannon's idea of information, a thing to build systems around. But there's a much more elegant definition of information that often gets attributed to him, although I haven't found a source for it. Stand by, if I find one I'll let you know. And at least philosophically, I think it contributes to our understanding. Information, he said, supposedly, is the resolution of uncertainty. Finally, let's talk about Professor Robert Losey out at UNC Chapel Hill. In his search for a definition that exists that can apply regardless of the discipline that one looks at, he gives us the idea of information from process. More specifically, information as the characteristics of a process's output that inform about the process itself. That process could be writing a book, or baking cookies, calculating pi, or looking at the stars. An interesting thing about this definition is that it pulls the definition away from being necessarily human-sourced. Losey spends an entire page discussing how a kitten's purr, for example, can produce many kinds of different information, depending on the lens through which one considers it. Maybe there's a place in LIS for a definition like this. It could give us the flexibility we need to cross the lines between computer science and psychology, or education and digital media, or user experience and social justice. But to be clear, Losey's idea is not as yet the information science definition. Such definition does not exist. And that's okay. Because LIS pulls from so many different fields, I think that there's something to be said for having some wiggle room in how information is described. My Chinese teachers always told me, 根据上下文找意思, which means find meaning according to context. And when we're looking at Dr. Bates's world of recorded information produced by human agency, the context matters. A lot. So that's just a few ideas of what information is, but there are tons more out there. If you want to see some of them, for example, go into the doobly-doo and you'll see a link to the entry on information from the Information Science Encyclopedia, written by our very own Dr. Bates, who I mentioned last video. Dr. Bates, you are getting so much coverage. Good on you. But I'm more curious to see how y'all decide to define information for yourself, whether that's for your studies or your work or your life more broadly. Let me know in the comments below or shoot me a tweet at StacksAtFacts and let me know, because yeah, I'd like to find out. If you liked what I did, thank you. Go ahead and actually like it on YouTube, reblog it, or do whatever you want with it. Share it with your friends. If you really liked it and want to see more stuff like this, go ahead and subscribe. Thank you for watching, and until next time, don't forget to ask questions. All right, bye.
Okay, do you like it? Let me reflect on this. I got totally lost when he was talking about Shannon and Professor, I didn't catch the name. I think the best philosopher in this case is our Cookie Monster. Yes, yes. Well, yes, exactly. Data and information. Long story short, data is the raw ingredients, or is the thing, right? But information, that is the process, the data. And you can see who played a role here. Cookie Monster. He added, he produce the information. Cookie is delicious. Cookie is delicious and crunch. Cookies are gone, right? Okay, then who equals to Cookie Monster in our GIS study?
Would this be us?
Yes, yes, exactly, bingo. That is GIS. GIS basically, you know, turn the data like this, like your spreadsheet. I just show you from Literati, from iNaturalist, from Purple Air to information you can get. Well, I don't need to do too much. For example, our Purple Air here, I just plot the data, right? And you immediately, you can see this system change that raw data into information, okay? So in other words, later in this study guide, okay, study guide, here, okay, you will have a live demonstration how to download data from US Census Bureau. You know, they are producing the latest census across the country, right? 2020 by the end of the year, but not sure whether they can do that due to the pandemic. But you can see how you download their data, raw data, and then how to process that and turn that to a map. Okay, to a map. So that is a very, you won't have a quiz on this, you know, it's just a practical thing. And warning, US Census Bureau changed the website, the interface. So don't try to, I know you have the tendency to try everything you see, you know, to make a map because you're map lovers, I know. But USGS, not USGS, US Census Bureau changed the website, okay? Here, just stay. Just, you know, watch the video to see how they turn the spreadsheet, download the spreadsheet and turn that to a map. And later we are going to have a lab to show you how to use their new website, okay? Yeah, just get the basic idea, Okay, so long story short, what is, you know, the, here, information and data, okay? You got it, Cookie Monster. Right? Cookie Monster help us to process the data to information, okay? All right, then we have the data. We need the location to mark that data is a spatial data, right? And we want to turn that data into a GIS data layer. We can pull that into our computer, okay? I always tell my students, okay, including you guys, don't be frustrated about the problems computer gives you, because computers, they're stupid. Computers are stupid. They just know 2 digits. There's no intelligence. You know, AI, that is artificial intelligence, but that is the people give our computer that intelligence. By itself, it just know 2 things. Let me annotate. That is 0 and 1. Okay? Then that is a problem, right? We have beautiful data. We have, you know, longitude and latitude, topology, semantic attributes, and time. We have so, you know, nice looking even the information and data. How can we communicate with our computers? And you can see in the video, the professor, he basically also show off his Chinese. 根据上下文猜意思. Do you know what that means? No, because you don't know the language, right? But he needed to translate that sentence to English. Okay, you need to guess the meaning in terms of, you know, in the context. Put the word into the context, and then you can understand it. Well, in that case, the same idea. We need to turn all these things to the language, to communicate with computer with the language computer know. Right? So that's the idea. So that is another thing. We call that representation. So we want to represent our data spreadsheet. Okay, some, you know, benchmark, some the pushpin, the markers you see on the map, and even our maps itself. You need to say that in a way computer can understand it. Okay, can understand it. So, well, representation. English is my second language, so I have to look it up on the dictionary. So in the dictionary, representation means the description or the portrayal of something or someone in a particular way or as a certain nature. It's so abstract and mouthful. It's a pen, right? But I know draw, right? I know depict. I know that one. It means draw. So I'm thinking, okay, this is the rock I see in West Quest Rock. You know, in that area, I see this perfect round, the boulder here. Okay, I want to depict, I want to draw it. I want to make a map for my field trip. Okay, so I draw it. I'm not a good painter or anything like that, close to that. I just draw a circle. But I know in our class, we have artists. We have artists. They may draw a fancy picture like this, right? Okay, you can see her representation is much better than me because it's close to the real one. But is it real? It's still not, right? So representation is an approximation of the real world. In GIS, we want to represent our spatial features. You will hear this word, this term a lot. Spatial features. Okay, that is the thing, the real thing you see on the ground in your real life, like, our 405, the highways, like swimming pool in Jeff's house, and the mountains. We call that spatial features, and we want to use geometric shape like this, okay, or a surface to represent our terrain, our land, right? It's a surface, like our ocean surface, right? To represent it, but it's impossible to make it 100% accurate, okay? It's just approximation, okay? All right, you can see, basically, this is a cool thing about our SMC campus. From 2018, we have this drone. We hire the drone companies to capture our campus, on the welcome day and the graduation day. It's very cool, so check it out. But this is the real world. But when you look at our campus on Google Map, you can see it's way more, simple, right? Way simple than the real world. So that is approximation, okay? So you can see here, that is your, your considerations when you try to turn your data to a GIS data layers. Later in lecture, actually next lecture, no, module 4, we are going to create our own GIS data. You're going to do one thing called digitizing, okay? So forget about it. You cannot do a perfect job, guys. Just relax, okay? Because the real world is too complex. When we want to turn that spatial feature to a data layer, you have to select the things you want to represent. For example, in the sandbox, right? The sand plane right here, for the military people, they may just want to represent the key things, in Afghanistan, right? The powerhouse or something they're interested. But when we turn our map, our real world, to a campus map, you probably just want to, represent or draw our buildings. You don't care the trees, the palm trees, right? Okay, so this is the selective, what to represent, and also simplification, the scale. Okay, you want to simplify. For example, our coastal line. You're out there, make a map for our Hilda Bay, right? Hilda Bay, here our Santa Monica Bay. You want to draw the coastal lines, right? Does the shape of our coastal line matters for Hilda Bay? Probably not, right? You can just draw a smooth curve to represent the shape of our Santa Monica Bay. But if you are a geologist or geomorphologist, you're going to study the coastal erosion. Okay, coastal erosion, how our waves, tides erode the beaches to cause the landslide in Palos Verdes because, millionaire houses over there, right? Then in that case, you probably need very detailed information about the coastal line, the shape, right? And also scale matters. When you zoom out, for example, you see it on the Google map. Let's see, Google map, there's a Google map. Google, Professor Google map. Okay, so you can see, when you zoom in, you probably want to show the details, right? Like our pier, like those storm drain down here, What's that? Okay, storm drain and many other details along our coast. But when you zoom out, for example, at this level, you can see, can you find our pier? No, right? It's smoothed out. So scale also matters, okay? All right, okay, let's see. Okay. Okay, time scale also matters. Time scale also matters. For example, you want to show people the cases of COVID-19. Last time on Thursday, we saw that curve, the accumulative the curve for COVID-19 on Esri. Still remember, like earthworms, okay? And if you want to show daily cases, you want to show more details, right? Okay, then you need to represent your data by days. But what if you want to show people just, the month by month since March, that is the start, right? And then April, May, June, July, how we, climb up and, winding down, right? So that is another story, another way to represent the data. Okay, so that is the key considerations when you represent your data into GIS software. Okay. All right. By far, any questions? Let me see the chat box. Cookie Monster. Yes, we loved it. Okay, let's see.
Professor G,
Yes.
I have a question, but it portrays to, I guess, allowing the community to input data. Is there sort of like a body that corrects that data so it doesn't become noise all the time? Or is it self-regulated?
That's a very, very good question. Yes. So yes, the answer is yes. Okay. So let me show you. First, you need a nationwide, even global-wide agency or organization to define the standards of the data. Okay, let me show you on the study guide. It's right here. Metadata. Okay, so this video will show you what is for our US. Okay, let me show you here. I think we have metadata here. Here, sorry, it's in our textbook. Okay, you're going to read number 2, the chapter 2. Let's see, metadata. Okay, metadata. Okay, here we go. Okay, so for US, this is the federal government. Okay, this is a Federal Geographic Data Committee, FGDC, to define the data standards for, people generate spatial data in US. In other words, USGS, US Census Bureau, labor statistic department, Department of Labor, they all follow this standard. Okay, globally we have that ISO, right? ISO or GEO ISO, and you have that. I forgot the exact name. Let me show you later. Okay, globally to allow people follow the same standard to generate the spatial data. Okay, otherwise it will be a chaos. Okay, and when we follow the data standards, we call that metadata. When, like, for example, your iNaturalist, they collect those data, well, they won't be immediately become the pushpins on the map. Okay, for example, those points, you and me, anyone can contribute it, including school kids. Actually, Natural History Museum, they have a few projects to allow teachers in, K to 12, the schools, to, organize their, their kids and to help collect the data about, frog or, snake or these things, okay? But they do have the experts in Natural History Museum to help process the data. Make sure those data is trustworthy, it's right. The longitude and latitude, they're right. It's not noise. It's not just I take a picture in my bedroom and then I just, make it up. No, that won't happen. So they process the data and then they turn that into a map. So that is why in GIS can also help you edit the data to filter out the noise. Another example I can give you is, satellites, right? Satellites, basically, they collect the data, basically those waves, like, NPR, KCRW, right? You have your radio waves, but sometimes if your signal is not good, well, you have some noise, right? Bear with me. Those are the noise, okay? Through one thing called data editing. Okay, data editing, you're going to smooth out those noises, and then you have good data to become good map. Don't forget, garbage in, garbage out. We definitely don't want garbage data into our GIS system. Sorry, it's a long answer for your question.
No, it's perfect. I just wanted to know that.
Thank you.
Yeah,
but
you answered
yes.
the question. Thank you so much.
But yes, that is, you need to process the data. So data creation and data pre-processing actually is very important. Down the road, we have another lab to download data from US Census Bureau. You will see they also have, some blanks. They don't have the information. Those are the things you need to, continue to process to filter that out. Otherwise, that will, make your map looks wrong. Okay. Yeah. Okay, wonderful question. And I see another longer question on the chat box, but let me read it later, okay? And we can do that during the office hour. Okay, so here, mouse, okay. Then data and information, and no matter how you try, right? You cannot represent the data perfectly, represent the real world perfectly, okay? Then let's shift the topic a little bit. Let's focus on that spatial feature we are going to represent. There's two ways actually to represent the real world, okay? So we call that two types of geophenomenon based on the spatial continuity. It's continuous spatially or it's not continuous, okay? So for example, in this case, I show you the picture about Hollywood. Okay, I hike a lot in this place. Okay, have you been to the top of the Hollywood sign? It's a cool hike, guys, but it will be very hot in these days. Okay, so one way I see the real world will be discrete spatial features or spatial objects. For example, the Hollywood sign. For example, this signal tower. Okay, for example, those houses. I say it's discrete because it's discrete. It's not continuous. They have a defined boundary in the space, right? You can draw. Oh, I'm sorry. Let me my phone. 喂，你好。哦，你要不给我放到前台吧？啊，对对对。好，哎，啊，好的好的，谢谢，嗯。So sorry, you probably just understand 谢谢。That is a package delivered to our house. We need to change the lights in our house. So sorry about that. Yes, discrete objects, that is the objects with defined boundary. For example, Hollywood sign, you have a defined boundary. Your house have a defined boundary. Our trail, our road have a defined boundary. You basically can draw a geometric shape that can be a point, can be a line, or if a swimming pool, you can draw a polygon, right? But there's another thing on this picture we haven't, talk about yet. That is our terrain. Like Grayson's question or mistake, why I say that's a beautiful mistake, okay? That is the surface. That is our terrain. You can see for our terrain, there's no boundary you can draw. You say, Jane, you're wrong. I can draw a boundary for the mountains. But how you define this is the end of the mountain? Is this road? Maybe a little bit downhill, right? Maybe people say, oh, we need to, go all the way to Hollywood, the city, on the street, when the elevation is 0. But there's no defined boundary for a mountain. It's just a continuous surface. You can see here we have our Hollywood, Santa Monica Mountains, and in there, that is our valleys, right? San Fernando Valley. And then back there, there's the mountains again, right? Okay, there's continue. Another example can be our ocean surface. You have those waves, right? Well, another invisible surface that can be our temperature surface. You have here, Southern California, super hot, right? If you think it's like higher elevation of temperature, you will have a peak. But if you go to inland, if you go to the north, you go to Minnesota, you go to Portland, right? You go to Canada, well, you will feel it's cooler and cooler. If you represent it with elevation, then that is a low elevation. It's a continuous surface. In terms of temperature, you cannot draw the border, right? You cannot draw the border. That is continuous surface, okay? So we have two things to represent. Then with a better, draw or depict those two types of, phenomenons or spatial features in different ways, right? So that is, well, another introduction why we need to have two basic data model, okay? So if you see yourself out there, you're more interested in those houses, Hollywood sign, the roads, you are going to use geometric shapes, okay? You just have 3, points, lines, and polygons, okay? Points and polygons for different geometric shape, okay? Well, but spatial scales matters, okay? But for example, when you zoom in, just draw the park, the Grace Park, right? You may want to use polygons to represent those houses because your scale is large. You want to show people a lot of details, right? But when you zoom out to produce a map for LA County, then you probably will use your points to represent those houses, right? It doesn't matter because at that level, no one can see my house, right? Or even you can, condense, merge, combine those houses into a polygon to show, oh, that is Hollywood, this community, right? Just use a polygon to show that community. You don't have to differentiate different houses, right? So that is scale matters. And the fields is really simple. You just need to imagine there's a fish net. You can just drip it on our real Earth surface, and you're going to collect the information in each square here. That is your grids or raster. Okay, so put them together. This is your real world. You can see if you are interested in the trees, houses, river in this case, okay, you have the defined boundary. You are going to use vector data model, okay? And here, if you're interested in, okay, the terrain or the land cover or temperature, you're going to drape this fish net on top of the earth, and you're going to collect the information for each square. That is just this simple, this data model, this idea, okay? But you can see, well, no matter which one you are using, you are still going to represent at least location and thematic attributes. Okay, at least location and thematic attributes. So here you can see in your vector data model how to represent location. You don't have to go into those rabbit holes, okay? I just want to show you the technique details. Actually, those coordinates, they're invisible to you in ArcGIS or QGIS. Okay, I just want to show you. The location basically is those pair of numbers. Okay, if you use a line, it's just a sequence, an array of those points. Okay, if there's a polygon, it's a still array, but the starting point and end point is the same. So you can close your polygon. Okay, close your polygon. Okay, well, at this point, and you can attach. Last time we see how attribute table, right, is generated, right? Each row like this, right? Each row represent one feature, like in this case, that is one state, and you have different attributes by columns, right? So you can see this is, you need to have an ID, okay? State name and different attributes, okay? But at this point, if you just have a table, have a, a way to record the coordinates, like you're going to do in lab, I think 3, digitizing. You basically just generate a model, have 2 pieces of information, location and thematic attributes, right? You don't have what? Spatial relationship means your river doesn't know, oh, I have a woods number 1 next to it. Okay, you don't know, okay, this house is to the south of these woods. Okay, so that is non-topological data model, which also means your data is messy. It's as messy as spaghetti. So people also call this model spaghetti data model, means non-topological data model. Okay, non-topological data model. So there is a common thing, common data file, okay? Data format is called shapefile or end with SHP, okay, for this non-topological data model, okay? And you will see in your normal folder, when you open the folder, contain this, the shapefile, you will see, oh my God, we have so many files. But let's take a closer look at it. They all share the same name, but with different, file extension. Okay, so here you can see this one end with SHP, right? This one you must have because what is stored in this file, guess what? That is your coordinates, shape. Okay, and here you can see you have another file. It's called DBF. It actually stands for database file. This is your attribute table. This is your attribute table. Actually, you can just drag this a hack. Okay, annotate here, here. You can actually drag this file to your Excel. You just open the Excel, you can drag it, and you can immediately see the attribute table. Okay, on Thursday, practical Thursday, let me show you. Okay, but you must have those 3. Okay, you must have those 3. This one, projection, that is the next module when we understand the coordinates and projection. Okay, this is the projection of the data. Okay, so this non-topological data model. Are we good at this point? I tend to talk very fast.
Professor Jean?
Yes.
I'm just trying to relate it with my my knowledge of, I guess, imaging.
Mm-hmm.
Would you say that the vector version of a map has more resolution than the pixelated square?
That is exactly right. Can you repeat that?
So it's just that the vector version of a map has a lot more resolution.
Exactly. So you
Pixelated.
can see, in other words, you totally get it. Vector data model, you have more accurate location data. Because you can see here later in my slides, you can also read on your by yourself. Okay, it's down there to compare different data models. Okay, this one you can see the raster, the grid, the size matters. We call that pixel size. For example, you have good old days. You have old smartphone, right? Maybe your grandma used old smartphone, and she took a picture. It's very pixelized. It's blurred, right? Same thing here. Why it's blurred in our, for example, satellite image? You have to, use one value to represent a larger area. For example, here, let me show you. Let's see. Let me show you this way. Find it. It should be like this, okay? You need to generalize because you can see when you have large cell size, large pixel size, you basically will lose the shape of your farm. See, like my farm look like a potato, right? Looks like potato. But when you use a larger cell size, it's look like this veg, or it's like what? T shape, okay? And for example, your road is okay, but looks like pixelized. So vector data model is better in terms of representing the location and the geometric shape, okay? If that really matter, like our coastal line, you want to study coastal erosion, landslide in Palos Verdes, you do want to pick up the vector data, the shape file. Okay, you don't want to use our satellite image because especially when the resolution is low, you will lose the true shape. That's a very good question. And also here, in your raster data model, another concern is, especially when the pixel size or grid size is too large, you have this, problem here. Okay, so for example, my pixel in this case is too large. I want to study the land cover of this area. And you can see here, this specific square cover two things, river and what? Like island, right? Okay, so it should be a land or it should be a river. I don't know, right? So this is a hard decision to make. And for example, in this case, should I represent it as a house or it's still grassland, right? And here, should it be, a tree or just a barren land? I don't know. There's no answer. Don't ask me, I don't know. You made decision. And you can see here immediately, guys, GIS satellite image can help us collect the data. GIS can help us collect the data, but in the process, in the data processing process, in data processing. Okay, let me delete this. We always, right, lose information actually, right? So for example, since I can only use one value to, assign to this pixel, I have to make a decision, trade-off, right? So I say it's a tree, I lose the information about the ground. If I say it's a house, I lose the information about grassland, right? There's all uncertainty, okay? There's uncertainty and errors associated with the data and information in GIS. So that's why in the video I shared with you earlier, information, data, when you turn the data to information, there's no 100% accurate. There's no 100% translation. Okay, so that is a concern in GIS. That is a concern in GIS. Okay. Any questions, guys? Okay, very good, actually. Let's see. Okay, and then, yes, let me directly go to the comparison, the side-by-side comparison on the very last slide. Okay, your team model is optional in this lecture. Okay, it's a little bit higher level, but it's cool to see. You can represent the map, represent the terrain surface using those triangles. Okay, maybe let me show you on Thursday. Okay, so vector model, team model, and the raster data model. Let's compare them. Okay, in terms of the complexity of the data structure. Okay, you can see vector is crying in terms of this because vector data model is a little bit complex. Okay, a little bit complex. As you can see in my lecture slides and also in the video you're going to watch on the study guide, it's very complex to compose, to build a data structure for vector. You need to build table, you need to, record the X and Y for each point. It's very complex, okay? And also, but for the raster data model, it's easy. It's just a bunch of, a fishnet, okay? You just need to record, the pixel size and your starting points, okay? But the data volume, your vector data is smaller. You probably have this experience. If you have, a vector data, like your vector picture, right? Vector picture, then the data size is smaller. But for your pixel raster picture, the data size will be large, okay? But the good thing for vector data model is it can represent very precise location information in a very precise way, but it's not for raster. Okay, and also it can help you define the topology, spatial relationship, but not for raster. Okay, not for raster. Okay, so in that case, depends on what you are going to do, guys. Depends on what you are going to do. You are going to make your decision. Raster is better or vector is better. Okay, my experience, if I do care, my project, the shape or the the size or the location really matters, I go for vector. If it's a continuous surface, okay, like our temperature, land cover, terrain elevation, then I will go with raster. Okay, raster. But you can always convert, between those two data models. Let's see, GIS can make that happen. Data processing. Okay, you can convert it. Those are the tools. You can use QGIS or ArcGIS to do this, but you always lose information when you do this. You can see you will lose the shape, especially when you turn your rivers from vector to raster, polygons to raster, right? And if you convert it back, you lose information again. Okay, you lose information again. So try to, avoid the data model conversion in your project because in data processing, you always lose information.
Maybe I missed this, but could you give an example of where you would use the 10 model?
Yes, okay. Then that's a perfect question, Lauren. You can see in our comparison like this, okay? Let me just, just use this slide, okay? So you can see, well, vector and raster, they both have their, pros and cons, right? Vector, they have, the precise location, but raster is really simple. It's very easy to capture, but raster can be redundant, okay? For example, in this case, let me show you this way, okay? So for example, our Hollywood, right? You have the mountains, but immediately you have this very flat area. very flat area. If you use raster data model to represent our terrain, okay, for the surface, you have to, place a fishnet, especially when you want very accurate information, the shape or the elevation of our land. Your pixel size will be very small, like our satellites. You can, pick up, half meter pixel size, but as a result, your data will be huge, right? It's not flexible, in other words. But your TIM model, if you use, those irregular TIM model represent triangulated irregular network, okay? See, here is the perfect solution. I can use very small triangles to represent those mountainous area. The terrain change very fast, drastically, right? But I can increase the triangle size for those flat area. In that area, I don't have to, collect too many points because they're all same, right? And then you can see, on one hand, you have this perfect, smooth surface, right? Continuous surface. On the other hand, you significantly reduce the data set, the data volume. Okay, you're going to use triangles instead of, the grids, the fixed grids to represent terrain. So to answer your question, Lauren, TIM model is very good for continuous surface again. Don't get me wrong, we still want to use the vector to represent our, discrete objects. But for continuous surface, especially when you want to, reduce the size of your files, you may want to turn that raster to TIM model. Okay, and
it almost. Oh, sorry, I was going to say it almost seems like it would be a good way to represent data collected from LiDAR. I don't really know much about LiDAR, but
exactly, Lauren. Exactly. If people don't know what LiDAR is, that is a laser. The laser signal send out the signal to your objects, and you have the reflectance. You basically have a cloud of points. Yes. Okay. And then you have those points. You can build those triangles, okay, to represent your terrain, the elevation, and that will significantly reduce the data set, the data volume. Another advantage of this TIM model is it's very easy to visualize in 3D. Okay, in 3D. Later, when we learn GPS and LiDAR down the road, the data collection in that module, I'm going to show you, okay, how to turn those points to a 3D model, just like this. It's very easy to use our TIM model to represent this 3D surface. Okay, but the rendering, the time for raster layer to render like a 3D will take longer because they have more pixels to be processed. Okay, so two things: smooth layer and also can reduce the data size, and it's very good at to show you the 3D. I hope that answered your question, Lauren.
Yeah,
Jane,
absolutely.
Do you want to use, should we use the raster model first and then the TIM model, like to choose between the two?
Yes, if your raster, actually, if you want to use raster to represent very detailed information. So for example, for our, let's see, let me give you an example. Every location matters, for example. Let's see. Right on my head, I cannot think of it. Maybe your land cover change very fast, over the surface. Here is, your alfalfa, for example, our farmland, okay? This part is alfalfa, next to it is, some weeds, or next to it is some trees, some grass, okay, in our Palmdale, okay? And next to it is a, pond. In that case, you probably want to use raster over TIM, okay? And another thing, I just got this idea. You inspire me, Paula. If you want to represent some, information about the type about name, we call that nominal information. Okay, it's just like this part is alfalfa. Next to it is wheats. Next to it is some grassland. Next to it is some barren land, for example. You want to represent those, nominal information. It's not, the numbers you can calculate, you can do the math. Then we prefer use raster instead of tin, because that tin is more for, elevation, temperature, and, those quantitative information, not for qualitative information. Okay. All right. Any other questions? Okay. Let's see. Okay. All right. I think that is a very, a little bit challenging, the concept for this lecture. Basically, that is a data model, because this concept is a little bit, abstract. Okay. But I do find our textbook, open source textbook, did a great job on this one. Really did a great job on this one. Okay, so you can see here. Let me close this. You have a lot of videos. Okay, if you open that link, you'll see the second chapter. Okay, they just have, the first section, 2.1 is the longest, but they really get the job done very well. Okay, to introduce you data and information, and I share with you one video already what's the difference between data and information. Okay, metadata is a description about the data. So basically that is the standards. Okay, FGDC or the ISO. Okay, and researching the data basically is when you're out there to download the data, what are the considerations? Okay, you have a study question on this. I want you to read this chapter. We probably don't have time to cover this in our lecture. Okay, just right. The next section is, our demonstration. Okay. All right. So on Thursday, our practical Thursday. Okay, we have Taco Tuesday today. Theoretical Tuesday. Okay, on our practical Thursday, I'm going to show you how you can use QGIS and ArcGIS. Okay, first to turn the data into GIS data layers, okay, and how to process the data to make a simple map. Okay, I also want to show you some tips and tricks how to do your lab 2 using QGIS and APRA. Okay. All right. So, any other questions? Oh, I see a few questions on the chat box. Okay, sorry. Okay. Can you see my chat box, or you can open your own chat box, right? Okay, APRA. Okay. So this is from Candice. Candice said, I have a question. I'm making a SOC stats, and we talk about stats a lot. So when we talk about stats, how do these stats translate into 4 stats? Like a location. Candice, are you here? I don't understand the question you put there.
Yes, I'm here. I just, because when obviously a lot of the statistics that we enter are from social stat people,
right?
But actually Evangelist helped me answer the question already.
Okay, yes. Evangelist just answered this question. Is about data analysis by variables, say variable A, ST. Yeah, this is software. Stats is a software, by the way. Okay, and here, how they're related, correlation. Yes, so basically what you played in your stats in a software, like in your Excel, that is your tables, right? You're still working with a spatial information. But if your table looks like this, looks like, share the screen, sorry, new share, my spreadsheet, okay? Looks like the thing I shared with you this, they contain longitude and latitude, okay? They contain, let me start my QGIS, for example. I know, this time let's show off the QGIS. QGIS. Okay, so while it's starting, let me show you this one. If they contain longitude and latitude, actually you can turn that to a GIS software, GIS data layer. You can see in GIS environment. Okay, so that is the way to turn that to a GIS data layer.
Yeah, that's kind of what I was asking. I was trying to ask because in my sociology class, like it's social stats, like they don't do, obviously they don't do GIS. They don't give us the longitude and latitude. So I was kind of asking like, how do I take that and put it in? But Vangelis kind of explained it, and it made sense the way he explained it. Like, obviously we would have to get the long and lat to put in there, and then we could make a 3D model of their 2D info.
Yes and no. Yes, you need to, for example, you download the data. Let me make a new spreadsheet here. File, new. Okay, so let me zoom into this. Data, view, sorry. For example, you download the data from US Census Bureau for LA County, okay, by each zip code. Okay, so you need a unique ID for each zip code. Okay, and then that is your zip code. Okay, and there's some attributes, for example, population, for example, percentage of, you know, white, okay, and percentage of, you know, Hispanic, okay, percentage of Asian, okay, percentage of African American, okay, or Black, okay, or Native American, and you know, percentage of Pacific Islander, right? And so on. You got my idea. I just want to show the breakdown of our ethnic groups. Okay, and you can see here, number one, that my number one zip code, for example, that is our school zip code. Okay, and population is blah blah blah, and breakdown is blah blah blah. Okay, and number two is the next to it, for example, this one, and you have different numbers. This is how you, with the data you download, you can put it in your stats, the software, right? Okay, and where's the location data? This one. In this case, we don't have X and Y, because what is a zip code? What is a zip code on the real Earth surface? Zip code is an area, right? And you see in our vector data model, well, you probably need a, you know, a loop of the coordinates of those here, these points, these points, these points, and these points to represent this zip code, right? It's very hard. I don't want to do that way, okay? All right, so here in your table, you actually have the location data, which is this zip code, because you know this number corresponds with a polygon in another data layer. In your zip code polygon layer, say this one, you have identifier, it's called 904.
Hey, Professor, real quick, we can't really see what you're doing. It's still on the litter one.
Oh, sorry. Let me stop here. Let me share just my screen. Thank you for letting me know. Do you see my spreadsheet? Yes, I'm sorry. Okay.
Yes.
Sorry. You should let me know, okay, if you cannot see. Okay, so you can see in this case, the data spreadsheet you download from U.S. Census Bureau, for example, you don't have that X and Y, right? Because you know our zip code on the real Earth surface is a polygon, okay? For example, this one is, 90404, and for this one is 90405. Okay, and you don't have, if you want to record the coordinates, you see that in our vector data model. You can see in order to record the coordinates of a polygon, you need to record, well, those corners, right? You need a loop of the coordinates. But you don't see that here. But your zip code in this case indicate the location, which you can use to combine this spreadsheet with your polygon. Because of what? Because you have these. You have the same identifier for your polygon, which is in another data layer. You can download it from U.S. Census Bureau. Okay, that's just a polygon data layer. Okay, and in your spreadsheet, in your A spatial data, you have the same information, see? And then I can link, I can join. It's called table join. That is later in our data editing and processing, actually next module, in your lab 3. You're going to do this. You're going to bring this standalone spreadsheet to the polygon, the attribute table, and you can combine, you can merge those two tables together. We call that table join. Okay, this is a very useful thing. We bring the richer information. Actually, this table join will also have a name called you enrich your attribute table. You enrich your attribute table by outside information. Okay, yeah. Candice, does that answer your question?
Yes, I'm sorry for skipping ahead. I didn't mean to. I was just I was like, wait a minute.
On Thursday, let me show you. We can download the table from, for example, we do have this cool project, in earlier the class to map out the homeless population. Okay, and Paula can help me on that because that's her project. We can download the data from, LAHSA, LA Housing Association, or association, and it's a spreadsheet. And we have the zip codes, or actually census tract. Hi, census tract. Just the polygons, and we through the table join, we can, merge two information together, and boom, we can make a map. Okay, so let me mark it on Thursday. Let me show you how to do this. Okay, that's a very, very good question. Okay, any other questions?
Are you having office hours after this?
Yes, after our meeting, I'm going to hold my office hours till 8:30. Okay, we can ask individual questions.
Okay.
Okay. All right, last but not least, let me show off QGIS. Okay, so you can see here, this if you open QGIS, it's just like this. Okay, it's a little bit, too much information here because I have done a lot of projects. Okay, but the things we just want to map out the trash litter, right? So you're going to add, let's see, layer, right? I want to create a layer based on my spreadsheet. Okay, add a layer, vector data layer, because your trash, they're push pins, right? Just individual observations, so should be vector. So that's why the series, the concept still, very important. Otherwise, you won't be able to use those software. What is vector? What is raster? What is the delimited layer, right? Okay, so add vector data layer. Okay, oh, I'm sorry. In this case, it should be this one. Add delimited text layer, actually. All right, so the file name, let me browse to my desktop. It's right here. Okay, and it's a CSV. Okay, here is the thing, guys. Here is the thing. Oh, I need to save it. Sorry. It's here. Okay, let's save that as. You see my spreadsheet, right? Yes. Okay. Let's save that as when you separate the longitude and latitude. You want to save that as comma delimited CSV or spreadsheet. Also work. Let's save that as CSV. That's basically the text file. Okay. And let's see here. Let me change the name. That is 2019 underscore on the safe side. Okay. Don't use hyphen. Use underscore always. 2020. Okay. Later report. Okay. Then let me close this. We are good to go. And I don't want to save this one. Okay, so let's go back to QGIS. Do you see my QGIS? Yes? Okay. Add a layer, add data layer, delimited. Okay, and I want to choose the other one, this one, CSV. Okay, so we have longitude, we have latitude, right, guys? Okay, so which one is your X? Which one is your Y? Think about it, it's just like, the X and Y, the Cartesian coordinate system. Okay, you learn in your geometry class. Okay, if you go this way, that is your X. If you go this way, that is your Y's, right? Okay, so if you change your location on the globe this way, you change from east, west. What's that? That is your longitude, right? If you go up and down, that is you go to the North Pole to the South Pole. That is the latitude, exactly. So X should be longitude. You can see QGIS is smart enough to identify it, right? And Y is your latitude. And you can see here, you need to specify the coordinate system. You need to specify if it's not longitude and latitude, it's some projected coordinate system, which we are going to learn later in a later module. You want to specify the right coordinate system. But since those information are captured by using your GPS on your smartphone, GPS, the satellites, they all use this one, WGS1984. Okay, so I just use this one. And then you just need to hit add. The layer name is okay. Okay, then you can close this. Here we go, guys. Let me add a base map. Oh, let's see, database or type it out in. I think it's the Earth or globe. No, okay, let me add a base map. Web, okay, services. Here, OSM, let's add OSM standards. Here we go, guys. This is our trash. This is our trash, the points. You can see, because we use that coordinate system, the shape, our Santa Monica is a little bit distorted. But in QGIS, you can see. It's weird. You can see here. Okay, definitely a lot on our beach. And what's here? 7th Street. A lot of people contribute information there. Oh, that is Wong's. Is that close to your house, Paula?
Huh? Oh, wait. Yeah, that's all the, wait, where is it? Sorry. Oh, bonds? Oh, yeah, because I picked up all that trash.
Okay. Thank you, Paula.
That data's so familiar because that's the one I picked.
Oh, okay.
It's literally the trail.
Oh my gosh, those data Paula helped us collected. And you can see, so kudos to Paula. Thank you, Paula. And you can see here, guys, now this data, GIS data layer, right? You can change the symbology, but you can see if you click on certain points, you can pull out the attribute data associated with it. You can see here, you have your liter, if they have the tags, right? And then longitude and latitude, country US, and date, which day is submitted. It's in August. Okay, that is Paula in her free time, help us collect those data. Okay, so that's it. That is, you know, how easy it is to turn your spreadsheet. We just, you know, collect it like this one to a GIS data layer. As long as you have this longitude and latitude for points, but for polygons, you need to do the table join. Let me demonstrate that on Thursday. Okay? All right. Okay, guys, that is for today. And my apologies, a little bit long, but I hope you learned something useful and fun. Okay, let me see, chat box, typo, zip code, clarifying. Yes, so Paula said zip code can serve as location for longitude and latitude. Yes, yes and no. Zip code is location information, okay, which can be linked, can be connected to that polygon. But that polygon have more than one longitude and latitude. Like in your data model, for a polygon, you need to record, for example, this very irregular polygon, you need to record all these turning points. We call that shape points. That is also why we call this model shapefile, right? We call that shape points. Okay, all right. So, any other questions before I let you go? Good, nice. Oh, we don't have this question for quiz 1. Since there's no time limit, does that mean we can open and close it, you know, as long as you want? Yes.
Okay.
Yes. Okay. So as long as you don't submit it, you can always keep it open. But let me know if there's an issue. You cannot, you know, keep your work. Let me know. I can reopen the quiz for you. Sometimes it's just a little glitch or here and there on Canvas. Let me know. Okay. It's open book. It's also, you know, no time limit. So take your time. My teaching philosophy is teaching for understanding. I'm not here to judge you. I'm not here to just like, you know, points distributor, you know, like hand sanitizer distributor, you know, to give you the points or deduct the points. I want to help you to learn, and everyone can learn. I believe that. There's no stereotype, okay? All right, let me know if you need any help and if you have any questions. If you have questions, you want to ask me individually, please stay. I do have my office hours. And otherwise, I will see you on Taco Thursday. No, actually, Practical Thursday. All right, bye, guys. Wish you a great evening. Bye.
Bye, Jen.
Bye.